The light-catching buckets on a sensor are not really pixels in the traditional sense, even though we all refer to them as pixels. They are more accurately referred to as sensors, or sensing elements, or sensors which capture light. Most cameras today use something called a Bayer filter system. A complete Bayer set is made up of 4 color-filtered sensors, 2 green staggered with 1 red and 1 blue. Think of a filter as a very small piece of colored film covering the light sensor. Its job is to prevent certain types of light from entering. So let me ask you this. What do you think happens when different colored light hits one of these colored filtered sensors? If a red filtered sensor is exposed to a bright blue or green light, the sensor cannot see it. However, red light can penetrate a red filter and the volume or the brightness of that light is recorded by the sensor. The camera's processor knows if any light penetrated the red filtered sensor, it can only be red, and therefore calculates that pixel as red light. So the color calculation happens in the processor, not by the sensor itself. Blue filtered sensors will only capture blue light, and green will only capture green. For the rest of this lesson, we'll use colored water to show you what the processor sees. Just remember, it starts out as an intensity of light, not a color. The information of red, green, and blue light, which makes up an image, is also referred to as channel information, or channels. Now I imagine you have several questions. You know that when you magnify an image, you see several colors, not just red, green, or blue, but you also see yellow and orange and aqua and purple and pink. So you're probably wondering, what in the world is going on? For every pixel we see in a digital image, 9 sensors are involved in the calculation. One central sensor, which would be the position of the target pixel, as well as the surrounding 8 sensors, which will contribute their information to the processor's calculation. Now just for fun, say central sensor 9 times as fast as you can. That should keep you busy for a little while. Now let's simplify this a little bit and instead look at 3 sensors, a red, green, and blue, with the middle sensor acting as the target pixel area. Now we already know that if the sensors are exposed to red light, the target pixel will be red. If the sensors are exposed to blue light, the target pixel will be blue. And you probably already guessed that if sensors are exposed to green light, the target pixel will be green. Okay, now those were pretty easy. What about yellow light? Well, yellow light is made up of both red and green light. The red and green sensors both capture light, and the processor knows that when this happens, the target pixel is yellow. Aqua light is made up of both green and blue light. Purple light, or magenta, is made up of both red and blue light. If the sensors don't catch any light, the pixel will be black. If the sensors are completely full, the pixel will be white. If the sensors have any equal amount in between those two, it will be a shade of gray. In fact, different amounts of red, green, and blue information can make just about any color of light. We know that in JPEG images, which use 8-bit depth, there are a total of 256 shades or intensities of light. If we were to calculate the total number of possible colors, it would be 256 red intensities times 256 blue intensities times 256 green intensities, which equal about 17 million possible colors. That's amazing. Now you can also see this in action using the color picker in Photoshop. The numeric values you see at RGB stands for the amount of red, green, and blue information used in calculating that specific color. Do you notice how these values stay between 0 and 255? Every time we pick a color using this swatch, we can see how much of each is used in the calculation. Black has all zeros, white has all 255s, and grays are all equal values. If we were to look at any other color, we can see how much each channel contributes to that particular color. Now, we don't think about it much when we're working in Photoshop, but when we're using its tools to make adjustments, what we're really doing is changing the pixel's appearance by reassigning the input information. We're changing these numbers. That's what Photoshop does when we make adjustments. And I think that's a pretty cool concept to know. I would probably say 90 to 95% of all photographers and Photoshop users really don't understand that this is happening in Photoshop. So hey, that's a good little conversation starter. Do you know how pixels get its color? Okay, you can talk about that at your next little photo meeting, whatever you guys do for that. The take-home message for this lesson is that every pixel gets its color from gathering red, green, and blue information from several stencils, and it's the processor that's able to piece this information together and decipher the proper color for a pixel. It's pretty much amazing, if you ask me. If you found this video helpful, you may be interested in my new DVD, Photoshop Crash Course. I'll not only teach you the most important tools in Photoshop, I'll teach you how to think in Photoshop. It can be ordered from the following link.